Principles, Session 3, Properties of Materials and Corrosion. So at the end of this part of the session, I want you all to be able to describe what is meant by elasticity, malleability, ductility, and tensile strength. We're also going to talk briefly about hardness as well and what that means. These are all properties of materials. I also want you guys to be able to tell me what causes degradation of plastics and explain how we can reduce or minimise this. Explain the difference between ferrous metals and non-ferrous metals, the ways that these can corrode and how we can prevent corrosion. So, properties of materials. Some materials have got a lot of elasticity, particularly plastics. When you bend them, they will return back to their original shape. And you can see a great example over here of elasticity. So if you have a spring, for example, made of one material, you pull that spring and then let go of it, it will spring back to its original shape, and that shows that it's got elasticity. It returns to its original shape. Some metals have got some degree of elasticity, that, and particularly low carbon steel. That's why we need to overbend it by about 5 degrees, because it will spring back due to elasticity. Also worth being aware of plasticity. Plasticity is when things don't spring back, and when you bend anything past its a point of elasticity, then it will suffer what's called plastic deformation. Essentially, it won't return back to its original shape. For example, if you took the same spring as before and you really pulled it much further, then it would still spring back, but it wouldn't spring all the way back, and it would have been said to have suffered from plastic deformation. And that's what happens when you bend metal pipes. When you'll sort of bend them round, and they'll go past the point they can spring back, and they'll sort of suffer what's called plastic deformation, and then they won't return to their original shape. So we're going to talk about malleability and ductility as well. Malleability and ductility essentially are reliant on plasticity. Once they are put under a certain type of force, then they won't return to their original shape. Malleability is when materials suffer plastic deformation. They change shape under compressive force, and the prime example of a very malleable material is lead. Lead's the most malleable material we're likely to work with as plumbers. Copper's malleable too. So is steel. Actually, steel has got some degree of malleability. If you hit steel with a hammer, for example, it would sort of move, change out of shape. But lead's the most malleable material that we need to be aware of. We're going to talk about ductility now. Essentially, ductility is when materials suffer plastic deformation. They change shape under a tensile load, which is a pulling load. And copper is the most ductile material that we need to be aware of. The prime example of that is when we get all these tiny, fine, thin threads of wire, which get then put together to create cables. And that's a result of the ductility of copper. It's a very ductile material. It can be drawn out into threads by pulling. Hardness, we're going to talk about. Hardness is essentially the resistance to penetration, resistance to scratching. Generally speaking, the harder material is, the less malleable or ductile it will be. And diamond is the hardest naturally occurring material on Earth. We sometimes might use diamond coatings on drill bits or on cutting blades to allow us to cut through other hard materials. There's 2 ways of measuring hardness. One is Mohs scale, which you can see up on the right hand side here, where you might use one material to see if it can scratch another material, and the other is the absolute scale of hardness, which is a bit more of a scientific kind of scale. thermal expansion. Well, we've talked previously about thermal expansion. All materials will expand to some degree when heated or cooled, they'll contract. But plastic expands far more than metals when heated. So we'll sort of bear that in mind when it comes to the test. Okay. Some plastics can actually be resoftened by heating. They can sort of be melted back down and recycled. And these types of plastic, this category of plastic, would be called a thermoplastics. And all of the pipework materials that we're likely to use, like polybutylene, polyethylene, polypropylene, PVC and ABS, are all categorized as thermoplastics. And like I say, they can be melted down and recycled. There are some plastics that can't be resoftened or recycled, and they're called thermosetting plastics. We don't generally use them so much anymore in the industry. In the past, they might have been used to make toilet seats, for example, or even cisterns, toilet cisterns. But generally speaking, we would use thermoplastics, maybe PVC for those these days. Another couple of things worth noting about plastics is we need to try and protect them from both light and oil, because both of these are known to degrade, to break down plastic. So ideally we should keep our plastic pipework boxed in, away from light and away from oil or oil-based products, for example, some pipe jointing compounds, which would break down the plastic. It's also worth noting plastic is a very good thermal and electrical insulator. Metals, on the other hand, are very good conductors of electricity and heat, with copper being an excellent conductor of both heat and electricity. And copper, tin, aluminium, gold, zinc, silver, iron, nickel, titanium, cobalt, lead, these are all pure metals, and they're generally speaking softer than sort of mixtures of metals. Essentially you can create new properties from metals by mixing them together, and when you mix metals together, this would then be known as an alloy. Some examples of alloys would be brass, solder, bronze, and steel. Steel is a mixture of iron and carbon. These are all alloys, all mixtures of metals. So metals can be categorized as ferrous or non-ferrous. Essentially, ferrous metals are metals that contain iron. I've mentioned here mild steel, low carbon steel, high carbon steel, cast iron, even sort of stainless steel to some degree, are all kind of ferrous. And generally speaking, with the exception of stainless steel, all of these ferrous metals will be subject to atmospheric corrosion or rusting when they're exposed to air and water. All ferrous metals would be magnetic as well. And we can prevent corrosion with ferrous metals, particularly in radiators, by painting them. We paint them on the outside, and to protect them on the inside, we would use a chemical inhibitor in heating systems. Pitting corrosion in radiators could be caused by various causes. The most likely cause is atmospheric corrosion. Essentially, the water in there, and any air that might be bubbled in the water, will start to corrode the water, corrode the radiators on the inside, which can cause pitting, but it also causes a buildup of sludge, a buildup of what's known as magnetite in the bottom of the radiators. And if this sludge is circulated, these little bits of iron oxide essentially are circulated around the system, they can actually sort of speed up the erosion of the inside of the radiators, which can also increase the pitting on the inside of these radiators. So a good way to minimise that is actually by using a magnet cleaner, magnet inside the the system to sort of try and pick up these particles as they flow around. To prevent the damage or atmospheric corrosion to the outside of our pipework or the outside of our radiators, we can paint them. We might use, say, an iron oxide, a red oxide paint to paint sort of steel pipes, or a sort of white waterproof radiator paint to paint the radiators, or well, whatever colour for that matter, really. But yeah, painting the outside of some pipes and materials could be a good way of preventing them from suffering from atmospheric corrosion. Now we're going to briefly talk about non-ferrous metals. Essentially, non-ferrous metals are any metals which don't contain iron. So basically every other metal apart from sort of iron and steel, really. Interesting point, quite often non-ferrous metals, some examples here are copper, zinc and lead, they don't corrode as easily as sort of ferrous metals, even though arguably they should be more reactive. And the reason for this is actually they react with the air initially, and that actually creates a barrier which kind of coats the metal, called a patina. They end up with an oxide coating. The oxygen reacts with the metal, and then it creates an oxide coating, a sort of thin protective coating, which actually stops any further corrosion. It creates a barrier between the air and the metal, and that barrier is known as a patina. And finally, we've talked about this previously as well, electrolytic corrosion. Both ferrous and non-ferrous metals can be subject to electrolytic corrosion, particularly if you put these two you put two metals together that are far apart in the electromotive series. I mean, for example, like copper and zinc, or copper and steel or iron. In both those cases, they're quite far apart in the electromotive series, so therefore the copper would sort of eat away. The more cathodic copper would eat away at the more anodic zinc initially, and iron as well, if the two of them are close together in close proximity. Okay. This can also happen in brass fittings. If you've got a mixture of brass and copper, sorry, I've got a mixture of copper and zinc, that creates brass. But what can happen is the brass can suffer from something called dezinkification, where the zinc is actually sort of leached out of the brass, which can cause it to leak. Essentially, it becomes weaker, and the water can then pass through it. Okay, now it's time for your task.